All right, chemistry, let's take a look at our video lecture for chapter 11, section 4. We're talking about effusion and diffusion. Now, this is something that you should have talked about in biology, and guess what? I know you did, so don't give me any of that guff. What I want you to be able to do after this video lecture, I want you to be able to state Graham's law of effusion. I want you to be able to determine the relative rates of effusion of two gases of known molar masses. And then lastly, state the relationship between the molecular velocities of two gases and their molar masses. All right, let's get started. So household ammonia is a solution of ammonia gas, right? NH3 in water. That's what it means to be a solution. You take that ammonia and you put it in water. That's what it means to be in solution, dissolved in water. But when you open a bottle of household ammonia, the odor of ammonia gas doesn't take long to fill the room, and I'm sure you know what that smells like. Gas molecules, including molecules of the compounds responsible for that smell, right? So like the ammonia, travel at very high speeds in all directions and mix very quickly with molecules of gases in the air in a process called diffusion. So you open that bottle of floor cleaner. Floor cleaner is something that very commonly has ammonia in it, have that ammonia smell. Diffusion is the movement of particles from regions of higher density to regions of lower density. And in biology, you would have heard the same definition with the difference of, instead of a density, they would have said concentration. In biology, they would say that diffusion is the movement of particles from a region of high concentration to a region of low concentration. Same concept. High concentration, high density, moving to areas of low concentration or low density. So gases diffuse through each other at a very rapid rate. This has already been talked about before. If I have two kind of gas clouds moving at each other, they simply pass through one another very, very easily with minimal interactions. Because again, remember one of the assumptions of the KMT is that gas particles are very, very, very far apart. The expansion that occurs from the liquid state to the gaseous state is on the order of about 1,000 times. And so these gas particles are very, very far away from each other. It's actually very rare that they would collide with one another. But remember, they're also moving very, very fast. Remember, another assumption of the KMT was that gas particles are in constant, random, rapid motion. They're moving very quickly. So gases will diffuse through each other, meaning they won't really react much at all. They'll diffuse through each other at a very rapid rate because they're in rapid motion. Even if the air in the room is very still, meaning there's no wind, there's no movement of the air, there's no circulation, there's no air coming through the air conditioning vents or the heater vents or anything like that. If the air is still, it would only be a matter of minutes before that ammonia smell would be evenly distributed throughout the room, right? Because the ammonia molecules are distributing themselves throughout the room. They're moving from an area of high concentration to an area of low concentration. That's diffusion. So, during diffusion, a substance moves through from a region of high concentration to a region of low concentration until the mixture becomes homogeneous. A homogeneous mixture, right, means the same type. Same type. That's what the word breaks down to. Homogeneous, same type. A homogeneous mixture is one that, if you were to take a sample of that gas, that mixture from any point in the container, it would be the exact same composition, right? It's not like in a chocolate chip cookie. If you take a bite out of a chocolate chip cookie, sometimes you do get a chocolate chip, sometimes you don't, right? The composition is different throughout that cookie in different parts of that cookie, right? Because the chocolate chip is concentrated. It hasn't diffused out to the rest of the cookie. That wouldn't be a homogeneous mixture. That'd be a heterogeneous mixture. But gases will go through diffusion until they become homogeneous. So that's diffusion. Let's talk about effusion. They're closely related. Effusion has this teeny tiny little caveat, teeny tiny little change. Effusion is the passage of gas particles through a small opening. And that's it, through a small opening. They're still wanting to move from areas of high concentration to low concentration. They just have to do it through a small opening. So that's your big red flag that you're talking about effusion anytime there is a mention of a small opening. The Scottish scientist Thomas Graham found that at constant temperature and pressure, again, you've seen this as a theme, at constant temperature and pressure, the rate of effusion of a gas is inversely proportional to the square root of the gas's molar mass. All right, so inverse. As one goes up, the other one goes down. What's inversely related here? The rate of effusion, the speed with which these gases effuse is inversely related to the gas's molar mass, meaning the heavier the gas is, the slower it's going to effuse. The smaller or lighter a gas is, the faster it will effuse. Now there is a square root in there, so don't forget about that. You'll see that when we actually show you the equation here in a moment, but it's an inverse relationship. This law also holds when one compares rates of diffusion of molecular speeds in general. There are some small little hiccups there, but in general, basically for our purposes, this idea, this relationship is also going to be the same for diffusion, not just effusion. Again, inverse proportionality. So let's take a look and see what we're dealing with here. The molecular speeds, velocity of A and velocity of B, of gases A and B can be compared according to Graham's law of diffusion shown below. Graham's law of diffusion states that the rate of diffusion of a gas is inversely proportional to the square root of that gas's density. So be aware that V right there is not capital V. So don't be thinking that you're going to take this M value here on the right and divide it by the V value on the left and you're going to get density, because density is mass divided by volume. That M is molar mass. It's not just pure mass, it's molar mass. And that V is a lowercase v. It is velocity. It is velocity, not volume. Graham's law of diffusion states that the rate of diffusion of a gas is inversely proportional to the square root of the gas's density. Okay, so we have the square root. Everyone is familiar with the idea of a square root. All right. Which means you guys already have some experience with this when we look at the equation for kinetic energy, 1/2 mv squared. Particles of lower molar mass, right, lighter, will travel faster than the heavier particles. The heavier particles will move more slowly. According to the kinetic molecular theory, gas particles that are at the same temperature have the same average kinetic energy. Therefore, kinetic energy of the two gases that are at the same temperature can be expressed as thus: mv squared, 1/2 mv squared, 1/2 mv squared. Because any two particles at the same temperature will have the same amount of kinetic energy, both of these equations, right, the 1/2 mv squared for A and the 1/2 mv squared for B, will be the same number. It's going to be the same value because it's the same kinetic energy, because we said it's at the same temperature. So if they're going to be the same kinetic energy, they're going to be the same value. That means that both of these equations are going to be equal to one another, and we can put this little equal sign in here. So again, molar mass multiplied by velocity squared. And here is where your square root comes from. Solving this equation for the ratio of speeds between velocity of A and velocity of B is actually what gives Graham's law of diffusion.
The rate of effusion of gas A over the rate of effusion of gas B is equal to the square root of the molar mass of gas B over the square root of the molar mass of gas A.
Thank you, Robot Lady. One thing I do want to point out here is when we get into this square root form, we have the rate of effusion of A as a numerator. A is on the denominator over here on the molar mass side. This is what I want to point out. You got to crisscross the A's and the B's for this relationship to work appropriately. So rate of effusion of A, A's on top, to rate of effusion of B, B's on the bottom, is equal to square root of molar mass B, which is now on the top, over square root of molar mass of A, which is now on the bottom. So be aware of that. Be aware of this and know it real well. So let's take a look at the sample problem. Again, I want you guys to try to plug and chug into the equation we just showed you, Robot Lady just shared with you. So let's see what we can do here. Oxygen molecules have an average speed of 480 meters per second at room temperature. At the same temperature, what is the average speed of molecules of sulfur hexafluoride, which is SF6? Again, look what the question has given us. They've given us a speed. Right? They've given us a speed for oxygen. Now, we need to remember that oxygen is a diatomic molecule. It's O2. And so we're going to have to calculate the molar mass of oxygen in order to do this calculation appropriately. Remember, O2 has a mass of 32 grams per mole because there are two oxygens there. Two oxygens. Now, at room temperature, at the same temperature, the fact that the problem has told us it's the same temperature means that it's going to have the exact same kinetic energy, the exact same amount of kinetic energy. So the relationship between this speed, this velocity, and this mass is going to hold true for something of a much larger mass, and therefore it should travel at a much slower speed. Let's see if that holds true. So let's take a look at what we know so far. We know the velocity of O2, which is 480 meters per second. We're being asked for the velocity of SF6. We don't know how fast it's going. We do know the molar mass of oxygen. It's 2 times 16 because 16 is the mass of one oxygen. And so the molar mass of O2 is 32.00 grams per mole. We add up all the atoms that are in SF6. There's 32 grams per mole due to the sulfur. There are 6 atoms that are each coming in at 19 grams per mole. So we add those up, coming in at 146 grams per mole. So let's plug these into our problem. So go ahead and press pause now and finish this out on your own. All right. So we're trying to solve for the velocity of sulfur hexafluoride. And so we're going to rearrange this equation to solve for velocity of SF6. And so the first move I'm going to do is get this velocity of SF6 by itself. And so I'm going to multiply both sides of this equal sign, right, left and right side. I'm going to multiply both sides by 480 meters per second. That's going to get this denominator to cancel out and go away. And I'll have this value multiplied by 480 meters per second. So that's why I have this look right here, right? So I have this square root set up from earlier in the problem multiplied by 480 meters per second. Now, the first thing I'm going to do is I'm going to try to get rid of this whole boogabaloo up here because this square root, to be perfectly honest, intimidates me and I want to get rid of it. And so I'm going to divide 32 by 146 and then take the square root of that. It turns out, if you guys have your calculators on you or you did this successfully, that calculation right there is going to be 0.47. So I haven't done anything with this 480 meters per second, so that's still there. 480 meters per second multiplied by 0.47. Throw that into the calculator. I come up with 220 meters per second. All right, chemistry, that'll do it for this video lecture. I will see you next period.